Right, let's do another proof by induction. This time, let's do the sum of the cubes. So let's look at the sum of the cubes. So we'll prove that 1 cubed plus 2 cubed plus 3 cubed and so on up to n cubed equals n squared times n plus 1 squared over 4. Before we do that, let's just note something a bit interesting about this, because of course this is n times n plus 1 over 2 all squared. And this is the sum of all the numbers from 1 up to n, the natural numbers from 1 up to n, squared. So if you take the first n natural numbers and cube each one, the sum of that is the same as taking all the sum of the numbers from 1 to n and squaring that sum, which is a bit curious, really. Anyway, let's prove it by induction. So what's the first thing that we do? First we check n equals 1. n equals 1, well the left-hand side is 1, left-hand side equals 1, right-hand side is 1 times 2 squared, which is 4, divided by 4, which is indeed 1. So it's true for n equals 1. So now we've got to do the induction step. Let's assume that the result is true for n equals k and deduce the next one up. So assume true for n equals k, i.e. that 1 cubed plus q cubed and so on up to k cubed really does equal k squared times k plus 1 squared over 4. So now we aim to show that it's true for n equals k plus 1. Well, if we write out this sum all the way up to k plus 1, then we've got the sum up to k plus an extra bit. Okay, so 1 cubed plus 2 cubed plus and so on. The second to last term will be k cubed, and then the last term is k plus 1 cubed. Right? Now we know what that bit is by the induction hypothesis, because we know that we've assumed that that equals that. So we know that this equals k squared times k plus 1 squared over 4, and then we just have to add this last bit on the end, k plus 1 cubed. So this is by the induction hypothesis. So the induction hypothesis is the bit that we assumed here. Okay, so this is where we've got to. Should we just write down over here somewhere what it is that we're trying to get? So I'll put this in blue. We're trying to get this expression for n equals k plus 1. So we're trying to get k plus 1 squared multiplied by k plus 2 squared divided by 4. That's the aim for now, okay? Put that in a blue box, hopefully you can see that. Right. So what can we do to this? Well, as soon as you see an expression like this, there are kind of two things that you might try to do. One is you might try to multiply out all the brackets. The other is you might try to factorize it. Now, which do you think is going to help us more? So, in a way, multiplying out all the brackets it's definitely going to work. If you multiply out all the brackets, you can definitely see what's going on. But we want it in a form that looks like this. So if we multiply out all the brackets, we're going to have to factorize it again afterwards. So the most sensible thing to do here is going to be to factorize it. So the first thing we probably need to do is put the whole thing over a common denominator, which is 4. So we'll get k squared, k plus 1 squared plus 4, k plus 1 cubed over 4. Now I hope I'm going to have enough space. Now let's factorize it. So we can take out k plus 1 squared as a factor, k plus 1 squared Now what have we got left? Over here we've got k squared, and then over here we've taken out k plus 1 squared, so what we'll have left is 4 times k plus 1. So we get 4k plus 4, and all that is over 4. Now I've run out of space, so I'm going to come over here. But what does this equal? Well, this is supposed to be a 4, isn't it? There, 4k plus 4. Well, this part here is equal to k plus 2 squared, and that's what we're aiming for, right? So we're there. So this does equal k plus 1 squared multiplied by k plus 2 squared, because k plus 2 squared is this bit on the right, divided by 4. So to finish this proof off nicely, we should say, so by induction, the result is true for all n in the natural numbers. So let's go over what we did. Here's the thing we're trying to prove. We started by checking the case n equals 1. Then we assumed it was true for n equals k, deduced the fact that it was then true for n equals k plus 1, and that showed us it was going to be true for all natural numbers, so we're done.